The massive explosion is an idea that has framed how we could decipher the universe, outlining the support of current cosmology. As defined by Einstein's theory, known in cosmology course readings, the immense blast was the moment the universe began its development, pointing to the origin of all matter, energy, and existence. This event happened roughly 13.8 billion years ago and sparked the colossal universe we observe today. However, recent improvements in cosmology suggest that the colossal explosion was not the very beginning. Rather, there might have been a stage before this enormous and comparable explosion, an important phase in shaping the universe as we know it. This pre-period is referred to as infinite expansion. One of the most interesting aspects of modern cosmology is the idea that before the hot, dense phase of the Big Bang, the universe underwent an unbelievably fast and dramatic growth. During this time, the universe duplicated its size at an alarmingly rapid rate. To understand how absurdly fast this expansion was, assuming the universe began smaller than an atom, it would have become unfathomably larger than the entire observable universe in a minuscule fraction of a second, a period known as inflation, which lasted just a quadrillionth of a second. Though short, this stage played a crucial role in the formation of the universe. When the inflationary stage ended, the energy driving this expansion was released into space, warming it up and creating the particles of matter that form everything we now see. In many ways, inflation is the forerunner of what we consider the Big Bang. While the hypothesis of inflation is widely accepted in cosmology today, many unanswered questions remain. For instance, we still do not fully understand the origin of inflation, what caused it to stop, or how long it lasted. These are open questions in cosmology, and answering them is vital for a better understanding of the universe's earliest moments. Prior to inflation, the universe was in a tremendously dense, small region of matter, often referred to as a singularity. From this point, evolution began, eventually leading to the formation of atoms, particles, stars, and galaxies. The idea that the Big Bang marked the beginning of everything is compelling, but modern cosmology presents a more complex picture. Some theories suggest that the universe underwent a phase before the Big Bang. During this stage, the expansion caused the universe to grow at an incredible rate, expanding in size by a factor of a trillion in a fraction of a second. This rapid expansion was driven by a strange energy structure that filled the empty space. When inflation ended, the energy that powered this expansion transformed into particles, warming the universe and leading to the hot, dense state we now associate with the Big Bang. Though the inflationary phase was cold and empty, it set the stage for the creation of matter and the universe we see today. More theoretical developments in modern cosmology bring forward the concept of eternal inflation. This hypothesis proposes that inflation didn't end everywhere at the same time. Instead, it halted in patches, creating a variety of pockets, each of which could be a universe in its own right. Our universe may be just one of these pockets. According to eternal inflation, there could be an infinite number of universes, each with its own laws of physics and constants. This is where the idea of the multiverse becomes significant, the notion that our universe is just one among many or even an infinite amount of universes. If this idea is true, it might explain why our universe is so finely tuned for life. In a multiverse, every possible combination of physical laws could exist in different universes, and we happen to live in one where conditions are perfect for stars to form, and for carbon, oxygen, and other essential elements to exist. While theories like eternal inflation and the multiverse remain speculative, the concept of inflation itself is grounded in observational evidence. The strongest support for inflation comes from the cosmic microwave background, CMB, radiation, the oldest light in the universe, emitted about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form. At that point, the universe became transparent, and this light has been traveling through space ever since. By studying the CMB, cosmologists can essentially take a picture of the universe as an infant. This light provides clues about the universe's earliest days, supporting the inflationary model. One of the most significant discoveries came from the European Space Agency's Planck satellite, which took detailed images of the CMB. These images revealed subtle temperature variations in the early universe, variations that align with predictions made by inflationary theory. This experimental evidence strengthens the case that inflation is not just theoretical, but a critical element in understanding the origins of the universe. Understanding the Big Bang, and what preceded it, requires uniting two major theories in modern physics, Einstein's general relativity and quantum theory. General relativity explains the large-scale structure of the universe, its behavior, galaxies, stars, and planets, while quantum theory describes the behavior of atoms and molecules on the smallest scales. To answer cosmology's deepest questions, what the universe is made of and where it came from, scientists must develop a theory that merges these two frameworks. This would allow us to comprehend not just the Big Bang, but also the conditions that caused it. Among the most astonishing aspects of the universe is its size. The most distant objects we can observe are about 47 billion light-years away, meaning the observable universe is approximately 94 billion light-years in diameter. Given that the universe is only 13.8 billion years old, this may seem odd. How can the observable universe be larger than the time it would take light to travel that far? The answer lies in the universe's ongoing expansion. As space expands, distances between objects grow, making faraway objects appear farther than the time it would take light to reach us. Most scientists agree that the universe extends far beyond the observable limits. In fact, it's possible the entire universe is infinite in size. What we can see is limited by the speed of light and the time since the Big Bang. There may be vast regions of the universe that we will never be able to observe. While it's possible the universe is infinite, the question remains, is it truly endless? Most scientists are cautious about this idea. If the universe is infinite, then there is no outside of it, it would continue endlessly. Even if the universe is finite, it's not necessarily meaningful to speak of what's beyond it. Beyond would imply something outside of space itself, which may not be physically meaningful. Similarly, the moment the universe was created remains a subject of intense study. The current best estimate is that the universe will continue expanding indefinitely, due to a mysterious force called dark energy, which is causing this expansion to accelerate. Before dark energy was discovered, scientists believed that the universe's expansion would eventually slow down due to the gravitational pull of matter. But now, we know the universe is speeding up, possibly forever. This realization, that the universe's expansion is accelerating, has fundamentally changed our understanding of the cosmos. Dark energy, which makes up about 68% of the total energy content of the universe, is still one of the greatest mysteries in modern physics. We don't yet know what it is, why it exists, or how it behaves over time. Some theories suggest that dark energy is a cosmological constant, a fixed energy embedded in the fabric of space itself. Others propose it could be a dynamic field, changing in strength as the universe evolves. Either way, dark energy plays a decisive role in determining the ultimate fate of the universe. If current trends continue, the universe will keep expanding faster and faster. Galaxies that are now visible will eventually move beyond our observable horizon, making the universe seem emptier with time. Billions of years from now, distant galaxies could vanish from view entirely, leaving only the local group of galaxies, including the Milky Way, visible. This scenario is sometimes called the Big Freeze or heat death of the universe. As expansion continues, stars will burn out, galaxies will fade, and the universe will become colder and darker. Over incomprehensible timescales, matter may decay, and black holes may evaporate through Hawking radiation, leaving behind a vast, empty cosmos, a sea of space with no structure, no stars, no light. But this is only one possible ending. Alternative theories explore ideas like the Big Crunch, where the universe might one day reverse its expansion and collapse back into a singularity. Others propose the Big Rip, a dramatic scenario in which dark energy becomes so strong that it eventually tears apart galaxies, stars, planets, and even atomic particles. There's also speculation about cyclical models of the universe, suggesting that the cosmos might go through endless phases of expansion and contraction. In such models, our Big Bang might not have been the first, and the universe we live in could be just one cycle in an eternal cosmic rhythm. Each of these scenarios attempts to answer the deepest questions. Where did we come from? Where are we going? Is the universe eternal, or does it have an end? While many answers remain elusive, one thing is clear: humanity stands at a remarkable point in history. For the first time, we have the technology, intellect, and ambition to peer into the very beginning of time and contemplate the farthest reaches of space. As we continue to study the cosmos, through telescopes, satellites, particle accelerators, and theoretical models, we move closer to unraveling the profound mysteries of existence. The story of the universe is still being written, and we are both its observers and participants, living on a tiny world in a vast, expanding sea of stars. There was indeed even a likelihood that the universe might stop expanding and begin contracting, resulting in a major crunch. However, dark energy seems to be pushing the universe apart increasingly fast. If this acceleration continues, the universe will never stop expanding, eventually getting to a point where, because they are so far apart, galaxies become segregated from one another. In this situation, the universe would become cold, lifeless, and exhausted. Stars would wear out, and worlds would float apart. Matter would ultimately rot. This is referred to as the major heat or freeze death of the universe. The narrative of the universe, from the enormous blast to its possible end, is one of the most improbable yet critical and complex stories in science. Despite the fact that we've gained an extraordinary amount of knowledge about the starting points of the universe through the hypothesis of expansion, as well as investigation of the cosmic microwave background, numerous inquiries remain unanswered. What caused expansion to start and end? What lies beyond the observable universe? Is there a multiverse, and if so, how many other universes exist? As researchers proceed to study the universe using new ideas and advanced theories that connect quantum mechanics with general relativity, we will undoubtedly gain a deeper understanding of these mysteries. The journey to comprehend the universe is continuous, and every discovery helps us get closer to answering the profound questions concerning our existence. The investigation of the universe's beginnings and structure isn't simply a logical endeavor. It also raises philosophical inquiries about existence, reality, and our place in the universe. One significant area of interest in cosmology is the nature of dark matter, which is believed to make up roughly 27% of the universe's mass-energy content. Unlike normal matter, dark matter does not absorb or reflect light, making it imperceptible, observable only by its gravitational effects on visible matter. Understanding dark matter is fundamental for grasping the development and evolution of galaxies. Research and observations have offered insights into dark matter's properties, but its exact nature remains elusive. Several candidates have been proposed, including weakly interacting massive particles, WIMPs, actions, and other exotic particles. However, up to this point, no direct evidence of dark matter particles has been found. The search continues through a combination of terrestrial experiments, astrophysical observations, and simulations modeling how dark matter impacts the large-scale structure of the universe. Another important area of exploration is dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy accounts for about 68% of the universe's total energy content. Its discovery was unexpected and has sparked numerous hypotheses, including the cosmological constant and dynamic fields like quintessence. Understanding dark energy is crucial, as it will determine the ultimate fate of the universe. Researchers in the field are focusing on its impact on cosmic structures and trying to determine whether it remains constant over time or evolves. In addition to dark matter and dark energy, the study of large-scale structure formation provides significant insight into the universe's history. Observations of the cosmic web, a vast network of galaxies, clusters, and filaments, have demonstrated how matter clumps together under gravity, forming the intricate structures we see today. Supercomputers are used to simulate these processes, helping scientists understand how these formations developed over billions of years. Astrobiology also intersects with cosmology, as scientists try to understand the conditions essential for life beyond Earth. The search for exoplanets, planets orbiting stars outside our solar system, has intensified, with thousands discovered over the years. Some of these exoplanets lie within their stars' habitable zones, where conditions may be right for liquid water to exist. By studying these distant worlds, researchers hope to learn more about the potential for life elsewhere in the universe and the factors that make a planet suitable for life. Finally, the role of fundamental physics in cosmology cannot be overstated. The search for a unified theory that combines general relativity and quantum mechanics remains a key challenge. Theories like string theory and loop quantum gravity aim to bridge these two domains, offering explanations for phenomena such as black holes and the early universe. As technology advances, so does our ability to observe and interpret the vast cosmos. Space telescopes like the James Webb Space Telescope are transforming our understanding of the universe by providing unprecedented detail of distant galaxies and cosmic events. These revolutionary observations bring us closer to unraveling the mysteries of the universe's structure, development, and ultimate fate. The study of the universe is a complex web of scientific inquiry and philosophical reflection. From the fundamental forces that shape cosmic structures to the search for extraterrestrial life, our exploration reflects humanity's enduring fascination with the cosmos. As we strive to answer these profound questions, we gain a deeper appreciation for the vastness and intricacy of the universe. This profound appreciation is not just rooted in curiosity, but in a deeper yearning to understand our origin, purpose, and place within the grand design. The cosmos, in all its magnificence, serves as both a mirror and a mystery, reflecting our questions back at us, even as we reach for answers. As our instruments grow more precise and our theories more refined, we find ourselves standing at the frontier of a new era in cosmic understanding. Missions to distant planets, surveys of the early universe, and particle collisions that recreate the conditions moments after the Big Bang. Each of these endeavors adds another thread to the intricate fabric of our cosmic narrative. Yet, with each discovery, new questions emerge. What is the true nature of time? Could the universe be cyclical, expanding and contracting through infinite epochs? Are we alone in the cosmic ocean, or merely one of countless civilizations scattered among the stars? These questions, while scientific in nature, touch the soul of humanity. They challenge our assumptions, stretch the limits of our imagination, and ignite a sense of wonder that transcends generations. In exploring the cosmos, we are also exploring ourselves, our capacity for insight, creativity, and connection. Cosmology, then, is not merely the study of distant galaxies or obscure particles. It is the story of everything, of time and space, of light and darkness, of chaos and order. It is the tale of the universe written in the language of science, yet infused with the spirit of philosophy and the poetry of existence. And though we may never answer every question or uncover every secret, the pursuit itself defines us. The act of searching, the restless hunger for understanding, is what makes us human. For in the cold silence between the stars, in the long shadows of distant worlds, and in the ancient light that travels billions of years to reach our eyes, we find meaning. And we continue forward, ever gazing upward, not only to know the universe, but to know ourselves.